Our next speaker, the last speaker of the morning before our panel, is again a friend and a mentor. I'm a bit older than most of these folks, but they are certainly academically mentors to me. And so I'm going to be pleased to introduce Dr. Langlotz. Kurt Langlotz is a professor of radiology, MD, PhD, and he is the director of the Center for Artificial Intelligence in Medicine and Imaging, the Amy Center at Stanford University. He is Associate Chair for Information Systems and a Medical Informatics Director for Stanford Healthcare. He is responsible for the computer technology that supports the Stanford radiology practice. The Amy Center develops artificial intelligence methods that enable computer systems to draw inferences directly from image information and associated clinical data, augmenting the skills of human imaging professionals. Dr. Langlotz has authored over 100 scholarly publications and the book, The Radiology Report, a guide to thoughtful communication for radiologists and other medical professionals. He led the development of the RADLEX standard terminology for radiology report information, a national standard for imaging exam codes, and a library of radiology report templates that has been downloaded over 5 million times. Dr. Langlotz is a past president of the Radiology Alliance for Health Services Research, the College of SIM Fellows, and the Society for Imaging Informatics and Medicine, and a former board member of the Association of University Radiologists, the American Medical Informatics Association, and the Society for Medical Decision Making. He currently serves as on the board of directors of the Radiologic Society of North America. Dr. Langlotz has founded 3 healthcare information technology companies, the most recent of which was acquired by Nuance Communications in 2016. So you've really had the opportunity today for the leadership of the ACR and the RSNA, the 2 major professional organizations for radiology. Kurt, come on down.
Thank you, David, for that kind introduction. It's really a pleasure to be here today. There's a lot exciting that's happening both in imaging and in AI here at Mount Sinai, so I'm very pleased to be here. What I want to do is to tell you about some of the work that is going on at Stanford and how it illustrates some of the themes that I think you'll see as artificial intelligence is permeated throughout medical imaging and the medical world generally. Briefly, my disclosures. I advise a few AI startups. Our department has support from some of the major vendors. Our school is supported by Google, and I'm on the board of RSNA, as David mentioned. So the themes: interdisciplinary collaboration, precision health, care transformation, radiologist augmentation, and public data sets. So we're going to go through a lightning tour through these themes today. The first gives me a chance to tell you about what's happening at Stanford. So we established 18 months ago the center that David mentioned. We now have, we just approved our 100th affiliated faculty across 20 departments and 3 schools, one of whom you just heard from, Greg Zaharchuk. We're very proud of that, and it really, the key insight to this center is the interdisciplinary nature of this field across particularly engineering and schools of medicine, which are right across the street at Stanford. We particularly, the engine of our research is what we call our boot camp. So we advertise for graduate students in our School of Computer Science, other technical schools who are interested in healthcare and have the machine learning background. They go through an application process, and ultimately we narrow down to about 20 students a quarter. At the beginning of the quarter, we have our clinician scientists with their data sets prepared come and talk about their compelling clinical problem, talk about the data set that they have ready, and say, please work with me. And the graduate students break up into teams and solve these problems that I'm going to tell you about going forward. So that's our first theme, which is just that collaborative nature of the field. That's the way that we solve these kinds of AI clinical problems. Next theme I want to illustrate, this is the first model that we built in our center, and this has to do with bone age. So when you're concerned about possible developmental delay in a child, you can take an x-ray of the child's hand. From the development of the bones in the hand and wrist, you can get a sense of the physiologic age of that child. You compare to the chronologic age, and you get a sense for whether there's developmental delay. The current state of the art for this process is a book, which you see there, Grulich and Pyle, which happens to be the highest grossing book ever published by Stanford University Press. But the book, so you page through the book, and the reference data in this book are made from 300 Caucasian children who grew up in Cleveland in the 1950s. and you look at the picture of the book, it says 7.5 years. If it looks similar to the image that you're looking at, you say, this must be a 7.5-year-old physiologic age, and that's your bone age. We thought this was ripe for innovation with AI, and so this is the work of David Larson from Stanford, one of our affiliated faculty. And we built an AI model and compared it to human radiologists. Here, lower bars are better, so this is the distance from the right answer, the consensus of experts. And you can see that the machine was doing a little better than 2 of the humans and about the same as 2 others. So we're getting human-level performance from this deep learning model. And here you see some of the explainability, the heat maps, class activation maps that show where the AI algorithm is looking, and it's looking at the right places. The reason I mention this and illustrating the theme is that this AI model, now that these models are so scalable, it used to take 4 years and a PhD to build one of these systems. Now with the right training data, in a matter of weeks, you can build a very accurate model. So you can imagine, rather than having one model that gives the right answer for Caucasian kids in Cleveland in the 1950s, you can tailor a model, and we know bone development is different across different ethnic groups. You could build a separate model for each individual demographic group. So yes, there are problems with bias in AI, but AI can also help to give more precise answers for precise patient groups, and that was certainly a theme of Mike Snyder's talk earlier today. Next theme, I want to use the work of Matt Lundgren. So this is chest radiograph interpretation. So he, with our boot campers, has developed a model. This is Andrew Ng's lab as well. Developed a model to detect the 14 most common abnormalities on a chest radiograph. And you can see here that the model is about the same as humans in 10. It's a little better in 1, and the humans are a little better in 3. So again, very close to human-level performance for chest radiograph interpretation. We just finished a clinical trial of that bone age model. The data is being analyzed now. This will be going into a clinical trial shortly, prospective trial, to prioritize our work lists at Stanford to look at normal versus abnormal and bring the abnormals to the top. The other ways that, oh, and here's some more detailed data. So you can see where the algorithm fell on many of these variables for detecting nodules and consolidations compared with residents and board-certified radiologists. The other area where we're planning to use this model is in an emergency department of a large integrated delivery system. That system is already using an algorithm to predict who has pneumonia and treat them accordingly. So they send off all of these tests that you see here. Which do you think is the last test to come back? It's the chest x-ray. They get the report from the radiologist. They actually do natural language processing of the report to see whether it tends to favor pneumonia or not, feed that into their algorithm, determine the probability or predict the probability of pneumonia, and then treat the patient accordingly. So we're using this algorithm, we will be using this algorithm to substitute for that radiologist's judgment to make it quicker, look immediately at the image, detect pneumonia, not pneumonia, and combine with these other data to decide how to treat that patient. The radiologist will still look at the image for nodules and to double check the algorithm, but interesting approach to change the way care is delivered outside the radiology department. The other way that this is being used is we've taken the model and retrained it to recognize the same abnormalities on photographs of film. Now, why would we want to do that? That's an old style technology. Well, it turns out that's the way radiology often is done in the 60% of the world which is underserved by radiologists. But cell phones are everywhere, mobile phones with cameras. They can take a photograph of that film, upload it to the algorithm, and the algorithm gives this bar graph on the right as to what the most likely possibility is. So for a general practitioner who's trying to decide whether to send a patient home to his family who may have tuberculosis, this is a really valuable tool that we're trying to develop. So care transformation outside the radiology department, I think that's another area you'll see thematically as we create a healthy AI ecosystem. The other theme is augmenting physicians. We've heard about that as well earlier today. So this is the work of Bhavik Patel and our boot campers, and this is the detection of ligament and meniscal abnormalities on MR of the knee. You see the ROC plot there. Up and to the left is high accuracy. That's magnified in the center there. You can see the red and orange X's are the unaugmented radiologists. So rather than think about comparing the model to radiologists, to physicians, here we said, let's see how physicians do with and without the model, how much it helps them. And you can see the red and orange are unaugmented, the blues are the augmented physicians. And you can see generally people are moving up and to the left or to areas of high specificity. So it's clear that the AI model is helping, the algorithm is helping with the detection of these abnormalities. This is the work of Kristen Yam, again with our boot campers, a model to detect vascular aneurysms in the brain. And again, the data on the lower right there shows that the vast majority of physicians are actually helped by the advice of the algorithm. So that's our next theme, AI augmentation. So AI does, in fact, often help, and the humans and the algorithm are detecting two different classes of disease. So the combination of the two is better than either one alone. I was fortunate enough to participate in a NIH workshop where we looked at what are the key foundational and translational research avenues that should be pursued in the days, weeks, and years to come. And this is the paper that resulted in, published in Radiology, and I want to take you through it. So here we have a patient on a scanner. That scanner produces some source data, raw data. It might be case-based data for MR, sinogram data for CT, list mode data for PET. We can use that data to reconstruct a better image. And it turns out this has been studied for many years, a lot of closed-form physics type solutions. These kinds of models that Greg just showed you are very powerful for this reconstruction process, and then for actually enhancing the images after they've been reconstructed, as Greg mentioned. Those images then get looked at by a radiologist. A report gets produced. There may be other data in the electronic medical record. That data can be extremely useful for labeling these cases and creating training data. So processing the radiology report, extracting information to automatically label cases, very powerful area where there are new research methods being produced. And the revolution that's happened in natural language processing over the last couple of years is equivalent or even greater than the progress that happened in computer vision back in the 2012, 13, 14 range. The kinds of models that typically have been built were built on something called ImageNet, which was put together by Fei-Fei Li, a professor at Stanford, a database of 14 million natural scenes, but they were downsampled to 256 by 256. Our data tend to be 4D, 3D, multi-channel, multi-modality, high resolution, so we need to think about how to create machine learning models that are suitable for these high complexity, high volume data. And then lastly, because these systems are likely to be working in combination with clinicians, explanation methods. How can we help the model develop methods that the model can explain how it came to its conclusions that can help the clinician interpret and use the actionable advice? The other part of this was a roadmap of this workshop was a roadmap for translational research. So now we've built the models. How do we bring these into the clinical realm? I'll just review for you. So there are needs for data sets for training. So how do we make more data available? That's really a key bottleneck for training, testing, and validating. We need standards for bringing these algorithms into the clinical setting. Software use cases, and ACR, as Keith said, has been really pioneering this, developing what are the problems that we should be solving first, and then a balanced regulatory framework, which we hope we can have from the FDA. I'm just going to highlight the first two here. So data sets. At Stanford, we've released now 4 data sets publicly. You can go to our website and find them. We have 2 more coming out shortly. The next one will be a data set of echocardiograms that will be labeled and available. NYU here in New York has released a data set of MR data for image reconstruction. The NIH actually led the way back in 2017, releasing about 100,000 chest x-rays, and we recently released with the MIMIC group at MIT 600,000 labeled chest radiographs. So all those data are publicly available. The nice thing is that many of the societies have run these challenges. So RSNA has, for the last 3 years, led clinically relevant challenges. Our latest one is the Hemorrhage Detection Challenge, which is going on now, $25,000 prize money. So please go ahead and take a crack at it. We have hundreds of teams have already signed up for this, and the winners will be announced at the RSNA annual meeting, which is in the week after Thanksgiving this year. Next, I want to talk about these standards briefly. So this is a snapshot of the logos of the more than 100 companies who will be exhibiting at the AI Showcase at the RSNA annual meeting this year. So this is an incredible, you could call it a bubble, it's an incredibly rich industry right now, many, many small and large companies who are interested in these areas. The problem we have is that those same vendors need to get into the clinical workflow. So I have here the logos of the PACS vendors, the companies that I use when I'm sitting in a reading room. What are the software applications that I'm using where I want my information to be presented to me? And so the standards are being developed now as to how these 100 vendors can get the results into those clinical workflows. A very difficult problem. Just in closing, I want to mention that we have work going on in radiology head to toe and different modalities and throughout the life cycle. And I want to introduce you to this concept of the life cycle. So test selection, we may have a clinician who's about to order an MRI of the lumbar spine, and we can use some of these methods to determine what the likelihood that that study will be positive. And that's useful information to know at the time of order. This image reconstruction, image enhancement that Greg showed you about can lower radiation dose, lower imaging times. Quality control. So I may have a patient who's moving or breathing in the scanner. The images are of suboptimal quality. That may not be noticed by the technologist until the radiologist looks at it 2 hours later. The patient's at home, the contrast has been excreted, and nobody's happy. So you can imagine embedding that into a device. Triage, I mentioned the algorithm. I'm an ICU, a chest radiologist. We get 100 ICU films every morning, and knowing which of those are positive and bringing those to the top of my list can be extremely useful application. Detection, we know that's been used for quite a while in mammography, and it's an obvious application of these techniques. Disease classification. So if I'm not a subspecialty radiologist, maybe I'm out of my comfort zone, I'm a chest radiologist, I see something in the bone, I can put a circle around it. Can you give me some information about what the most likely diagnostic possibilities are? And then reporting, so just making sure that we document appropriately those critical findings that we see in our radiology reports. So I hope that gives you a flavor, a way of thinking about the themes that you're likely to see emerge as we move into this new world where AI is applied to medical imaging. Thank you very much.